Close your eyes for a moment and imagine the universe getting bigger. What did you picture? Maybe galaxies flying outward through space, like shrapnel from an explosion. Maybe the edge of the cosmos pushing into some vast empty void. Perhaps you imagined the universe as a sphere growing larger, displacing whatever existed beyond its boundary. Every one of these images is wrong. Completely, fundamentally wrong. And that is precisely what makes this question so extraordinary. The universe is expanding, but it is not expanding into anything. There is no outside, there is no edge, there is no void waiting to be filled. The expansion of the universe operates according to principles so alien to our everyday experience that even thinking about it properly requires us to abandon nearly every intuition we have about space, time, and reality itself. Right now, at this very moment, space is stretching. The distance between distant galaxy clusters is growing larger, not because those clusters are racing through space away from each other, but because new space is continuously appearing between them. Space itself is being created, woven into existence, expanding the cosmic fabric in every direction simultaneously. And this has been happening for nearly 14 billion years, ever since the moment we call the Big Bang. If you find this difficult to comprehend, you are in good company. When Albert Einstein first derived his equations of general relativity in 1915, he found that they naturally predicted a dynamic universe, one that must either expand or contract. This prediction so disturbed him that he modified his equations to force a static, unchanging cosmos. Einstein, the revolutionary who had already overturned our understanding of space and time, could not accept that the universe itself might be evolving. A decade later, when Edwin Hubble's observations proved the universe was indeed expanding, Einstein reportedly called his modification "my greatest blunder." But even then, even after accepting the observational evidence, physicists struggled with what expansion really meant. The question, what is it expanding into, became one of the most frequently asked questions in cosmology, asked by students, by the public, by scientists in other fields who encountered this strange idea. And it remains one of the hardest questions to answer, not because we lack knowledge, but because the answer requires us to think in ways our brains were never designed to think. The human mind evolved to navigate three-dimensional space at human scales, to track objects moving at human speeds, to understand the world through our senses. We did not evolve to grasp the nature of space-time itself, to visualize four-dimensional geometry, or to comprehend expansion without displacement. Think about how remarkable this is. Throughout history, humans have extended their understanding of the cosmos by analogy to familiar experiences. The Earth was like a disk because that is what the land looks like when you stand on it. The stars were like fires because they produced light. The planets were like wandering travelers because they moved against the fixed background of stars. Gravity was like a pulling force because that is what we experience when we lift objects. These analogies were often wrong, but they provided a starting point for understanding. The expansion of the universe breaks this pattern completely. There is no familiar analogy that captures what is really happening. Every comparison we make imports assumptions that lead us astray. The universe is not like bread dough rising in an oven, even though we often use this comparison, because dough expands into the space of the oven. The universe is not like an explosion sending debris outward, even though we call the beginning the Big Bang, because explosions occur within pre-existing space. The universe is not like a balloon inflating, our favourite teaching tool, because balloons expand into the surrounding air. Each of these analogies fails at the same critical point. They all assume something outside, some larger container or framework within which the expansion occurs. And for the universe, there is no such thing. The universe is not expanding into anything because there is nothing for it to expand into. This statement sounds paradoxical, even nonsensical, because our language and our conceptual frameworks were not built to handle it. Consider the word expansion itself. In every context you have encountered it before this moment, expansion meant something growing larger by occupying space that was previously filled with something else, or at least by extending into available space. A city expands into the countryside. A company expands into new markets. A gas expands to fill its container. Water expands when it freezes, cracking pipes and breaking rocks. In each case, there is a clear before and after, a region that was empty or occupied by something else, that becomes filled or occupied by the expanding thing. The universe does none of this. It is not filling space that was previously empty because there is no space outside the universe. It is not displacing anything because there is nothing to displace. It is not growing into available room because there is no room beyond it. The expansion of the universe is an expansion of space itself, and space is all there is. This is the core insight that makes the question, what is the universe expanding into, simultaneously natural and unanswerable. You're about to embark on a journey through one of the most mind-bending concepts in all of physics. We will explore what expansion really means when there is nothing to expand into. We will confront the limits of language, visualization, and perhaps even human comprehension. We will discover that the universe is not just stranger than we imagine, but stranger than we can imagine. And by the end, you will understand why some of the smartest physicists in history have wrestled with this question, and why the answer reveals something profound about the nature of existence itself. We will see how observations of distant galaxies shattered our assumptions about a static cosmos. We will follow the mathematical trail that led Einstein to predict an expanding universe, a prediction he initially rejected. We will examine the fabric of spacetime itself, learning how space and time are woven together and how that fabric can stretch and curve. We will peer into the first moments after the Big Bang, when the universe underwent the most dramatic expansion in cosmic history. We will grapple with the possibility that the universe might be infinite, which creates its own bizarre implications for what expansion means, and through it all, we will repeatedly confront the same humbling truth. The universe operates according to principles that transcend human intuition. Our brains evolved to navigate three-dimensional space at human scales, to throw spears accurately and climb trees successfully. We did not evolve to intuitively understand four-dimensional space-time or the intrinsic expansion of spatial geometry. The fact that we can understand these things at all using mathematics and careful reasoning is a testament to the power of human thought. But we should not expect to visualize them the way we visualize a tree or a mountain. If you are ready to have your conception of reality fundamentally altered, hit that like button and subscribe. We begin our descent into the cosmic mystery now. For thousands of years, humans have gazed upward and wondered about the cosmos. Ancient civilizations crafted elaborate mythologies to explain the heavens. Greek philosophers debated whether space extended infinitely or terminated at some crystalline sphere. Medieval thinkers puzzled over what might lie beyond the stars. But none of these questions quite captures the peculiar paradox we face today. The question, what is the universe expanding into, sounds reasonable at first. After all, when a balloon expands, it pushes outward into the surrounding air. When a city expands, it sprawls into the countryside. When water freezes and expands, it displaces whatever occupied that volume before. Expansion, in every context we experience directly, involves something growing larger by occupying space that was previously filled with something else. The expanding thing displaces the medium around it. There is always an inside and an outside, an edge where one region ends and another begins. This pattern is so universal in human experience that our brains automatically apply it to the universe. We cannot help ourselves. The moment someone says the universe is expanding, our minds immediately conjure an image of the cosmos as a thing with boundaries, pushing outward into some larger container. We might picture it as a bubble growing in an ocean of empty space, or a sphere of matter spreading through an infinite void. These visualizations feel natural, intuitive, obvious. They are also completely incorrect, and this is where the question becomes genuinely impossible in a fascinating way. The universe is not a thing inside something else. It is not a region of space filled with stuff surrounded by a region of empty space without stuff. It is not expanding into a pre-existing volume. The very concepts of into and outside require a spatial framework that extends beyond the thing you are describing, and no such framework exists for the universe. The universe, by definition, is everything that exists. All of space, all of time, all of matter and energy. There is nothing outside of it because outside is a spatial relationship, and all of space is contained within the universe itself. The history of how we arrived at this understanding is a story of repeatedly shattering comfortable assumptions. In ancient times, most cultures placed the Earth at the center of everything. The sky was a dome or a sphere, and the stars were lights embedded in that sphere, or perhaps holes through which divine light shone. The universe was small, comprehensible, centered on humanity and our home. The ancient Greeks made the first significant challenge to this view. Philosophers like Democritus and Epicurus proposed that the universe might be infinite, filled with countless worlds beyond our own. But other thinkers, particularly Aristotle, argued for a finite geocentric cosmos. Aristotle's view dominated for nearly 2,000 years, partly because it aligned with religious teachings, and partly because it matched immediate observations. After all, we do not feel the Earth moving, so it must be stationary. The Copernican revolution began to change this. Nicholas Copernicus proposed that the Earth orbited the Sun, not the other way around. This was not just a technical adjustment, it was a philosophical earthquake. If the Earth was not the centre of the universe, then maybe humans were not as special as we thought. Galileo's telescopic observations confirmed the heliocentric model and revealed that the Moon, Jupiter, and other celestial bodies were physical worlds like Earth, not perfect ethereal spheres. But even Copernicus and Galileo still believed in a finite universe, bounded by a sphere of fixed stars. It was not until the 20th century that we realized the true scale of the cosmos and the nature of its expansion. This realization came from a combination of theoretical physics and observational astronomy, each pushing the other forward. This is not just a technicality or a semantic trick. It represents a fundamental shift in how we must think about reality. When Edwin Hubble discovered in 1929 that distant galaxies were receding from us, with more distant galaxies moving faster, he revealed that space itself was expanding. Not objects flying through a static void, but the very fabric of space stretching, carrying galaxies along with it like raisins in rising bread dough. This discovery required physicists to abandon comfortable intuitive notions about space and embrace something far stranger. The bread dough analogy is useful but limited. Dough expands because yeast produces carbon dioxide gas, which creates bubbles that push the dough outward. The dough rises within the confines of a bowl or a pan, expanding into available space. But the universe has no yeast, no confining container, no available space to expand into. The analogy breaks down at precisely the point where it matters most. The question, what is the universe expanding into, persists because our language fails us. The word expanding automatically implies expansion into something. The word universe sounds like it should have an edge, a boundary, a place where it ends and something else begins. But these are artifacts of how human language evolved to describe everyday phenomena on human scales. When we try to apply this language to cosmology, it breaks down. The universe is expanding, yes, but not into anything. Space is getting bigger, absolutely, but there is no external space for it to grow into. Consider the challenge this poses to human cognition. We are three-dimensional creatures. We navigate a three-dimensional world. We understand concepts like left and right, up and down, forward and backward. We understand containers and contents, insides and outsides, boundaries and edges. These concepts are hardwired into how we perceive and think about reality. But the universe is a four-dimensional space-time, and some of its properties, like expansion, cannot be properly understood using three-dimensional intuitions. When physicists talk about the expansion of the universe, they are describing something that happens in four-dimensional space-time, and our three-dimensional brains simply cannot visualize it accurately. We can describe it mathematically, we can measure its effects, we can make predictions and test them, but we cannot picture it in the way we can picture a tree or a galaxy or even a black hole. Throughout history, scientists have grappled with similar failures of intuition. People once believed heavy objects must fall faster than light ones, because that is what intuition suggested. They thought the Earth must be stationary, because they could not feel it moving. They assumed time flowed at the same rate for everyone, everywhere. Each of these intuitions turned out to be wrong, and in each case, discovering the truth required accepting that reality operates according to principles far removed from everyday human experience. The expansion of the universe represents perhaps the ultimate example of this pattern. It is not merely counterintuitive, it is almost inconceivable. Our minds literally cannot form an accurate visual picture of what is happening because our visual and spatial reasoning evolved to navigate three-dimensional space at human scales. We have no mental machinery for properly imagining four-dimensional space-time or for visualizing a finite, yet unbounded three-dimensional space. We can describe these things mathematically, we can make predictions about them, We can test those predictions and find them correct, but we cannot truly picture them in the way we can picture a tree or a planet or even a distant galaxy. This is humbling but also profound. The universe is under no obligation to conform to our intuitions. Reality existed for billions of years before humans evolved the capacity to ponder it, and it will continue existing long after we are gone. The fact that we can understand the universe at all, even if we cannot always visualize it, represents a triumph of human reasoning. We have developed mathematics as a tool for grasping truths that exceed the reach of our senses and imagination. The expansion of the universe, properly understood, is one of those truths. So as we proceed, remember this. You will not be able to form a perfect mental picture of what is really happening. That is not a failure on your part. It is a limitation built into human cognition. What you can do is understand the principles, grasp the mathematics, and recognize when your intuitions are leading you astray. You can replace faulty visualizations with accurate concepts, even if those concepts feel abstract. And in doing so, you can genuinely comprehend something true about the cosmos, even if you cannot quite see it in your mind's eye. The ancients looked at the night sky and saw gods and heroes written in the stars. Medieval astronomers saw crystalline spheres carrying planets in perfect circles. Early modern scientists saw a clockwork universe, mechanical and deterministic. We now see something far stranger, a dynamic, evolving space-time that expands without expanding into anything, that curves and stretches according to mathematical laws, that began in a singular moment and will continue evolving for trillions of years. Each generation's picture of the cosmos reflects not just what we observe, but the limits of what we can conceive. And our picture, however strange, is still constrained by the architecture of human thought. When astronomers say the universe is expanding, they mean something very specific and very strange. They do not mean that galaxies are flying away from each other through space. They mean that space itself is stretching, and galaxies are embedded in that space, carried along by its expansion like markers drawn on the surface of an inflating balloon. This distinction is crucial. If galaxies were simply moving through static space, we could ask where they started and where they're going. We could imagine plotting their trajectories backward to find a point of origin. We could wonder what lies beyond the region they have reached. But that is not what is happening. Space between galaxies is literally growing larger. New space is continuously coming into existence between every pair of unbound objects in the universe. How do we know this? The evidence comes from light itself. When light travels through expanding space, its wavelength gets stretched along with that space. This stretching shifts the light toward the red end of the electromagnetic spectrum, a phenomenon called redshift. In the 1920s, astronomer Edwin Hubble measured the light from distant galaxies and found that nearly all of them showed redshift. Moreover, he discovered a pattern. The farther away a galaxy was, the more its light had been redshifted, and therefore the faster it appeared to be receding. But measuring cosmic expansion required solving a fundamental problem. How do you measure distances to objects billions of light years away? You cannot use a ruler. You cannot use parallax, the apparent shift in position as the Earth orbits the Sun, because that only works for nearby stars. You need a cosmic distance ladder, a series of measurement techniques that build on each other, each extending your reach deeper into the universe. The first rung of this ladder involves direct geometric measurements. For nearby stars, astronomers use parallax. As Earth orbits the Sun, nearby stars appear to shift position relative to more distant background stars. The amount of shift depends on the star's distance. Closer stars shift more, distant stars shift less. By measuring this shift precisely, astronomers can calculate distances out to a few thousand light years. The next rung involves standard candles, objects whose intrinsic brightness is known. If you know how bright an object truly is and you measure how bright it appears from Earth, you can calculate how far away it must be. The challenge is finding objects whose intrinsic brightness you can determine reliably. This is where Henrietta Leavitt's discovery became crucial. In the early 1900s, Leavitt studied Cepheid variable stars, stars that brighten and dim in a regular pattern. She discovered that the period of variation, how long it takes a Cepheid to go through one brightness cycle, is directly related to its intrinsic luminosity. Brighter Cepheids pulsate more slowly, dimmer ones pulsate faster. This relationship means Cepheids are perfect standard candles. Observe a Cepheid, measure its period, and you immediately know its intrinsic brightness. Compare that to how bright it appears, and you can calculate its distance. Leavitt's discovery, which she made while working as a computer at Harvard College Observatory, was one of the most important contributions to astronomy in the 20th century, though it took decades for her to receive proper recognition. Edwin Hubble used Cepheids to revolutionize our understanding of the cosmos. With the newly constructed 100-inch telescope at Mount Wilson Observatory, the largest in the world at the time, he could observe individual Cepheid variables in spiral nebulae. These nebulae had been debated for decades. Were they clouds of gas within our Milky Way galaxy, or were they separate galaxies far beyond our own? Hubble's observations of Cepheids provided the answer. The Cepheids in these spiral nebulae were incredibly faint, which meant they were incredibly distant, far too distant to be part of the Milky Way. The Andromeda Nebula, for example, was revealed to be about 900,000 light-years away. The number was later revised to about 2.5 million light-years as measurement techniques improved, but the conclusion was the same. Andromeda was a separate galaxy, comparable in size to the Milky Way. The universe was suddenly far larger than anyone had imagined. What we thought was the entire cosmos, our Milky Way, was just one galaxy among countless others scattered through space. The philosophical implications were staggering. If there were billions of galaxies, each containing billions of stars, the possibility of other worlds, other life, became not just plausible, but probable. But Hubble did not stop with distance measurements. He began studying the spectra of these galaxies, looking at the specific wavelengths of light they emitted. Hydrogen, helium, oxygen, and other elements produce characteristic spectral lines, specific wavelengths where they absorb or emit light. These lines are like fingerprints, allowing astronomers to identify which elements are present in a distant star or galaxy. What Hubble found was astonishing. The spectral lines from distant galaxies were shifted toward the red end of the spectrum. The shift was systematic and predictable, and when Hubble plotted the redshift against the distance, he found a linear relationship. Galaxies twice as far away had twice the redshift. Galaxies 3 times farther had 3 times the redshift. This linear relationship, now called Hubble's law, was the key evidence for cosmic expansion. If galaxies were moving through static space in random directions, you would not see this pattern. Some would be moving toward you, showing blue shift. Others would be moving away, showing red shift. The velocities would be random, unrelated to distance. But Hubble's law showed that recession velocity increased linearly with distance, exactly what you would expect if space itself were expanding uniformly. The implications were profound. If the universe is expanding now, it must have been smaller in the past. Much smaller, infinitely smaller at some finite time ago. This led to the concept of the Big Bang, though the term itself was coined later by Fred Hoyle, ironically as a dismissive criticism of the theory he opposed. The Big Bang was not an explosion in pre-existing space. This is a common misconception that the name unfortunately encourages. The Big Bang was the beginning of space itself, the moment when the universe emerged from an infinitely dense, infinitely hot state and began expanding. Before the Big Bang, there was no space, no time, no before. The concepts break down at that singularity. Modern cosmology has refined and extended Hubble's work dramatically. We can now measure distances to galaxies billions of light-years away using multiple techniques. Type Ia supernovae serve as even brighter standard candles than Cepheids, visible across billions of light-years. The cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old, allowing us to trace the expansion history back to nearly the beginning. The expansion rate, quantified by the Hubble constant, has been measured with increasing precision. Current best estimates put it at approximately 73 km per second per megaparsec, though there is a persistent tension between different measurement methods that cosmologists are working to resolve. This number tells us how fast space expands. For every 3.26 million light-years of distance, space expands at a rate that adds 73 km per second to the apparent recession velocity. This relationship, now called Hubble's law, reveals something profound. If we lived in a static universe where galaxies were simply flying through space due to some initial explosion, we would not expect to see this pattern. We would expect galaxies to be moving in various directions at various speeds, with no systematic relationship between distance and velocity. But Hubble's law tells us that every galaxy we can see is receding from us, and the recession velocity increases with distance. This is exactly what we would expect if space itself were expanding uniformly in all directions. Imagine drawing dots on the surface of a balloon and then inflating it. As the balloon expands, every dot moves away from every other dot. If you stand on one particular dot and measure how fast the other dots are moving away, you will find that dots twice as far away are moving twice as fast. This is not because those dots have higher velocities through the rubber of the balloon, but because there is more expanding rubber between you and them. The same principle applies to the universe. Galaxies that are twice as far away have twice as much expanding space between us and them, so they appear to recede twice as fast. This expansion is happening everywhere in the universe simultaneously. It is not centered on Earth, or on any other particular point. From every vantage point in the cosmos, every observer would see distant galaxies receding according to the same pattern. This is because the expansion is a property of space itself, not a motion of objects through space. The uniformity of this expansion is remarkable and essential to understanding cosmology. Imagine you are an astronomer in a galaxy 5 billion light-years from Earth. When you observe the universe from your vantage point, you would see distant galaxies receding from you in all directions, with recession velocity proportional to distance, just as we see from Earth. There is no special location, no cosmic center, no privileged reference point. Every location in the universe experiences the same expansion pattern. This might seem paradoxical at first. How can every point be the center of expansion? The answer lies in understanding that expansion is a property of space itself, not a motion through space. When space expands, every region expands simultaneously. Picture an infinite rubber sheet with dots marked on it. As you stretch the sheet uniformly in all directions, every dot sees every other dot moving away, with more distant dots moving faster. No dot is special. The expansion is a collective property of the entire sheet. The same applies to our three-dimensional universe. Space expands uniformly, and every observer, regardless of location, sees the same pattern of recession. This is called the cosmological principle. The universe is homogeneous and isotropic on sufficiently large scales, meaning it looks the same everywhere and in every direction when you average over large enough volumes. The expansion rate is quantified by a number called the Hubble constant, which tells us how fast space expands per unit distance. Current measurements put this value at approximately 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, so this means that for every 3.26 million light-years of distance between two objects, the space between them expands at a rate that adds 73 kilometers per second to their apparent separation speed. Let's unpack what this means in practice. Consider two galaxy clusters that are 326 million light-years apart, which is 100 megaparsecs. The space between them is expanding at a rate of 7,300 kilometers per second. That is about 2.4% of the speed of light. Now consider two clusters 3.26 billion light-years apart, 1,000 megaparsecs. The space between them expands at 73,000 kilometers per second, about 24% of the speed of light. At even greater distances, the expansion rate exceeds the speed of light. Objects that are approximately 14 billion light-years away are receding from us at the speed of light. Objects farther than that are receding faster than light. This sounds like it should violate special relativity, which states that nothing can move through space faster than light. But there is no violation because the objects are not moving through space faster than light. Space itself is expanding, and there is no speed limit on how fast space can expand. This creates one of the most profound features of our universe: cosmic horizons. Because space expands faster than light at sufficient distances, there are regions of the universe from which light can never reach us. No matter how long we wait, no matter how powerful our telescopes become, we will never observe these regions. They are beyond our cosmic event horizon, causally disconnected from us for all future time. The observable universe, the region from which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years. This is larger than 13.8 billion light-years because space has been expanding during the time light has been travelling toward us. A photon emitted from a galaxy when the universe was young has been travelling for nearly 13.8 billion years. but the galaxy that emitted it has been receding the whole time due to expansion, so it is now much farther than 13.8 billion light-years away. The cosmic event horizon, by contrast, has a radius of approximately 16 billion light-years. Beyond this distance, space is receding so fast that light emitted now will never reach us, even given infinite time. This horizon represents the ultimate boundary of what we can ever interact with or observe. Galaxies beyond the event horizon are, for all practical purposes, in separate universes, even though they are part of the same space-time. At small scales, this expansion is utterly negligible. The space between you and this screen is expanding, but at such an infinitesimal rate that all the expansion happening in the lifetime of the universe would not budge the atoms in your body by a fraction of a millimeter. Gravity, electromagnetism, and the other fundamental forces that hold matter together easily overcome the expansion at these scales. Even at the scale of our galaxy, or our local group of galaxies, gravity binds structures together strongly enough that expansion has no measurable effect. This is important to understand because it addresses a common misconception. People sometimes worry that if space is expanding, everything must be expanding, including atoms, people, planets, and galaxies. They imagine being stretched apart as space grows. But this is not what happens. The expansion of space is a general relativistic effect that operates on the larger scales, where gravity is too weak to bind structures together. Think of it this way. Gravity creates potential wells in space-time. Objects within these wells, whether they are planets orbiting a star or stars orbiting in a galaxy, are bound together. The expansion of space tries to push them apart, but gravity pulls them back. On small scales, gravity wins overwhelmingly. The electromagnetic forces holding atoms together are even stronger, billions of times, stronger than the gravitational effects of cosmic expansion. Consider our solar system. The sun's gravity keeps the planets in orbit. The expansion of space does exert an infinitesimal outward pressure, but it is completely negligible compared to the sun's gravitational pull. The planets do not spiral outward due to cosmic expansion. Their orbits remain stable. Similarly, our Milky Way galaxy is held together by the combined gravity of hundreds of billions of stars plus dark matter. Expansion cannot overcome this gravitational binding. Even galaxy clusters, structures containing hundreds or thousands of galaxies bound together by gravity, resist expansion. The Virgo cluster, for example, contains about 1,500 galaxies within a region roughly 15 million light-years across. The mutual gravity of these galaxies keeps them bound together. Individual galaxies within the cluster orbit the cluster's center of mass, occasionally, colliding and merging, but the cluster as a whole does not expand. Only at scales of hundreds of millions of light-years, where the gravitational pull between objects becomes very weak, does expansion dominate. At these scales, there is nothing binding galaxy clusters to each other, so the expansion of space carries them apart. The space between clusters grows, new space appears, and the clusters recede from each other. This creates an interesting phenomenon. Within a galaxy cluster, galaxies are gravitationally bound and do not participate in the expansion. But between clusters, expansion pushes them apart. The universe is therefore not uniformly expanding everywhere. It is more accurate to say that unbound regions of space are expanding while bound regions remain coherent. The expansion also affects light in a fascinating way. As a photon travels through expanding space, the space itself stretches, and the photon's wavelength stretches with it. This is the redshift we observe. A photon emitted with a wavelength of 500 nanometers, green light, might arrive at Earth with a wavelength of 1000 nanometers, infrared, if the universe has doubled in size during the photon's journey. This stretching of light is not a Doppler shift in the conventional sense, though it is often described that way. A Doppler shift occurs when a source is moving through space toward or away from an observer. The classic example is a siren's pitch changing as an ambulance drives past. As the ambulance approaches, sound waves are compressed, increasing the frequency and pitch. As it recedes, waves are stretched, decreasing frequency and pitch. The expansion redshift is different. The source galaxy is not moving through space, or at least, its motion through space is negligible compared to the expansion. Rather, the space between the source and the observer is growing, carrying the photon along with it, stretching its wavelength as space stretches. The photon itself does not change. It simply rides along in expanding space, and its wavelength expands with that space. This distinction becomes critical when considering very distant galaxies. Some galaxies are so far away that the space between us and them is expanding faster than light. The recession velocity calculated from redshift can exceed the speed of light. This does not violate special relativity because the galaxy is not moving through space faster than light. The space itself is expanding, and there is no speed limit on how fast space can expand. Astronomers measure redshift using the symbol Z, which quantifies how much wavelengths have been stretched. A redshift of Z1 means wavelengths have doubled, so the universe has doubled in size since the light was emitted. A redshift of ZR2 means wavelengths have tripled, so the universe has grown to 3 times its size when the light was emitted. The most distant galaxies observed have redshifts greater than ZR10, meaning the universe has expanded more than 11-fold since those galaxies emitted the light we now see. These high redshift galaxies appear as they were when the universe was less than 600 million years old, just a few % of its current age. They show us cosmic history, revealing how galaxies formed and evolved in the early universe. Their light has been travelling for over 13 billion years, and during that time, the universe has expanded dramatically, carrying those galaxies to distances of more than 30 billion light-years from Earth. This leads to another profound implication. Because the expansion rate is constant per unit distance, objects that are sufficiently far away will be receding from us faster than light can travel. Light from such objects will never reach us, no matter how long we wait, because the space between us and those objects is growing faster than light can traverse it. This creates a cosmic event horizon, a boundary beyond which we cannot observe anything, not because of any limit in our telescopes, but because of the fundamental structure of spacetime itself. The story of how we discovered this expansion is itself remarkable. In the early 1900s, most astronomers believed the universe was static and unchanging. The prevailing view was that our Milky Way galaxy was the entirety of the universe, and that the fuzzy spiral nebulae visible through telescopes were clouds of gas within our galaxy. This changed dramatically in the 1920s. Henrietta Leavitt, working at Harvard College Observatory, discovered a relationship between the brightness and pulsation period of a type of star called Cepheid variables. This relationship meant Cepheids could be used as standard candles to measure cosmic distances. By observing how bright a Cepheid appeared, and knowing how bright it actually was, astronomers could calculate how far away it must be. Edwin Hubble used the newly constructed 100-inch telescope at Mount Wilson Observatory to observe Cepheid variables in what were then called spiral nebulae. He discovered these nebulae were far too distant to be within our galaxy. They were separate galaxies, island universes in their own right, scattered throughout space at distances of millions of light years. The universe was suddenly far larger than anyone had imagined. But Hubble did not stop there. He began measuring not just the distances to these galaxies, but also their velocities. He did this by examining the spectra of light from galaxies, looking at the specific wavelengths emitted by hydrogen and other elements. What he found was astonishing. Nearly every galaxy showed a redshift, meaning their light was shifted toward longer, redder wavelengths. This redshift could only mean one thing. The galaxies were moving away from us, and when Hubble plotted the velocities against the distances, he found a linear relationship. Galaxies twice as far away were receding twice as fast. This was not random motion. This was systematic universal expansion. The implications took time to sink in. If every galaxy is moving away from every other galaxy, and the recession velocity increases with distance, then the universe itself must be expanding. Space is stretching, carrying galaxies along with it. Running this expansion backward in time leads to an extraordinary conclusion. The universe must have been smaller in the past, much smaller, infinitely smaller at some finite time in the past. This was the birth of Big Bang cosmology. Georges Lemaitre, a Belgian priest and physicist, had actually proposed the idea of an expanding universe emerging from a primeval atom before Hubble's observations confirmed it. Lemaitre derived the expansion from Einstein's equations of general relativity, showing that a static universe was unstable and that the equations naturally predicted expansion or contraction. Einstein himself initially resisted this conclusion. He believed the universe should be static, eternal, unchanging. To make his equations produce a static universe, he added the cosmological constant, a repulsive force that balanced gravity. When confronted with evidence of expansion, Einstein removed the constant and allegedly called it his greatest blunder, though historians debate whether he actually said this. The expansion of the universe revolutionized cosmology. It meant the universe had a history, an origin, a beginning. It meant the cosmos was not static but dynamic, evolving according to physical laws. It opened up entirely new questions. How did the expansion begin? What came before? What is the ultimate fate of the expanding universe? At small scales, this expansion is utterly negligible. The space between you and this screen is expanding, but at such an infinitesimal rate that all the expansion happening in the lifetime of the universe would not budge the atoms in your body by a fraction of a millimeter. Gravity, electromagnetism, and the other fundamental forces that hold matter together easily overcome the expansion at these scales. Even at the scale of our galaxy, or our local group of galaxies, gravity binds structures together strongly enough that expansion has no measurable effect. This is important to understand because it addresses a common misconception. People sometimes worry that if space is expanding, everything must be expanding, including atoms, people, planets, and galaxies. They imagine being stretched apart as space grows. But this is not what happens. The expansion of space is a general relativistic effect that operates on the larger scales where gravity is too weak to bind structures together. Think of it this way. Gravity creates potential wells in spacetime. Objects within these wells, whether they are planets orbiting a star or stars orbiting in a galaxy, are bound together. The expansion of space tries to push them apart, but gravity pulls them back. On small scales, gravity wins overwhelmingly. The electromagnetic forces holding atoms together are even stronger, billions of times, stronger than the gravitational effects of cosmic expansion. Only at scales of hundreds of millions of light years, where the gravitational pull between objects becomes very weak, does expansion dominate. At these scales, there is nothing binding galaxy clusters to each other, so the expansion of space carries them apart. The space between clusters grows, new space appears, and the clusters recede from each other. This creates an interesting phenomenon. Within a galaxy cluster, galaxies are gravitationally bound and do not participate in the expansion. But between clusters, expansion pushes them apart. The universe is therefore not uniformly expanding everywhere. It is more accurate to say that unbound regions of space are expanding while bound regions remain coherent. The expansion also affects light in a fascinating way. As a photon travels through expanding space, the space itself stretches, and the photon's wavelength stretches with it. This is the redshift we observe. A photon emitted with a wavelength of 500 nanometers, green light, might arrive at Earth with a wavelength of 1000 nanometers, infrared, if the universe has doubled in size during the photon's journey. This stretching of light is not a Doppler shift in the conventional sense, though it is often described that way. A Doppler shift occurs when a source is moving through space toward or away from an observer. The expansion redshift is different. The source galaxy is not moving through space, or at least its motion through space is negligible compared to the expansion. Rather, the space between the source and the observer is growing, carrying the photon along with it, stretching its wavelength as space stretches. This distinction becomes critical when considering very distant galaxies. Some galaxies are so far away that the space between us and them is expanding faster than light. The recession velocity calculated from redshift can exceed the speed of light. This does not violate special relativity, because the galaxy is not moving through space faster than light. The space itself is expanding, and there is no speed limit on how fast space can expand. This leads to another profound implication. Because the expansion rate is constant per unit distance, objects that are sufficiently far away will be receding from us faster than light can travel. Light from such objects will never reach us, no matter how long we wait, because the space between us and those objects is growing faster than light can traverse it. This creates a cosmic event horizon, a boundary beyond which we cannot observe anything, not because of any limit in our telescopes, but because of the fundamental structure of space-time itself. But at cosmological distances, involving hundreds of millions or billions of light years, the expansion becomes dominant. The space between galaxy clusters is genuinely growing, with new space appearing between them. Over billions of years, this accumulated expansion has carried clusters that were once relatively close together to distances so vast that their light takes eons to reach us. Here is another critical point. The expansion itself is not a speed in the conventional sense. Objects cannot move through space faster than light. This is a fundamental limit imposed by special relativity. But space itself can expand at any rate whatsoever. There is no cosmic speed limit on the expansion of space, because nothing is actually moving through space in the conventional sense. This is why we can observe galaxies whose recession velocities calculated from their redshift appear to exceed the speed of light. They are not actually travelling through space faster than light. The space between us and them is simply growing at a rate that produces an apparent separation velocity greater than the speed of light. This leads to another profound implication. Because the expansion rate is constant per unit distance, objects that are sufficiently far away will be receding from us faster than light can travel. Light from such objects will never reach us, no matter how long we wait, because the space between us and those objects is growing faster than light can traverse it. This creates a cosmic event horizon, a boundary beyond which we cannot observe anything, not because of any limit in our telescopes, but because of the fundamental structure of space-time itself. The expansion also means that the universe has a history. If space is stretching now, then it was smaller in the past. Tracing the expansion backward in time leads to a moment when all the space we can now observe was compressed into an infinitesimally small volume. This is the Big Bang. Not an explosion in pre-existing space, but the moment when space itself began expanding. Before that moment, there was no space, no time, no before, in any meaningful sense. The Big Bang marks the origin of space-time itself. Understanding expansion in these terms dismantles the naive picture of galaxies flying through space. It reveals that what is really happening is far stranger and more fundamental. Space is not a passive stage on which cosmic events play out. It is an active, dynamic, evolving entity. It stretches, bends, warps, and curves in response to the matter and energy it contains. And this brings us to one of the most revolutionary insights in the history of physics. In 1915, Albert Einstein published his general theory of relativity, and with it, he fundamentally changed humanity's understanding of gravity, space, and time. Before Einstein, these concepts were treated as separate, absolute entities. Space was the three-dimensional stage on which events occurred. Time was the universal clock that ticked forward at the same rate for everyone. Gravity was a mysterious force that somehow reached across empty space to pull objects together. Einstein revealed that all of these intuitions were wrong. Space and time, he showed, are not separate. They are woven together into a single, four-dimensional continuum called space-time. This is not just a mathematical abstraction or a convenient way of doing calculations, it is the actual structure of reality. Events in the universe are not located at a particular place at a particular time. They are located at particular points in four-dimensional space-time, and the separation between events involves both spatial distance and temporal duration. Moreover, Einstein demonstrated that space-time is not rigid and unchanging. It is flexible, dynamic, capable of being bent and warped by the presence of mass and energy. This warping of space-time is what we experience as gravity. When you drop a ball, it falls not because the Earth exerts some mystical attractive force, but because the Earth's mass warps the space-time around it, and the ball follows the curved path through that warped space-time. As physicist John Wheeler famously summarized, matter tells space-time how to curve, and curved space-time tells matter how to move. Visualizing four-dimensional space-time is impossible for human brains evolved to navigate three-dimensional space. We can, however, use analogies. The classic analogy involves a rubber sheet stretched taut. If you place a heavy ball on the sheet, it creates a depression. Smaller objects placed nearby will roll toward the ball, not because the ball exerts a force, but because the sheet is curved and they are following the contours of that curvature. This is similar to how planets orbit the Sun. The Sun's mass creates a deep curvature in space-time, and planets move along curved paths through that curved space-time. But this analogy has severe limitations. A rubber sheet is a two-dimensional surface embedded in three-dimensional space. The curvature requires that third dimension to curve into. Space-time, by contrast, is four-dimensional and not embedded in any higher dimensional space that we know of. Its curvature is intrinsic. meaning it exists without reference to any external dimension. This is nearly impossible to visualize, which is why physicists rely on mathematics to describe it rigorously. The mathematics of general relativity reveals something remarkable. Space-time is not just curved by matter in static ways. It can also be dynamic, changing over time in response to the distribution of matter and energy. In particular, Einstein's equations allow for solutions where space-time itself expands or contracts uniformly throughout the universe. This was initially so counterintuitive that Einstein himself resisted it. He added a term to his equations, the cosmological constant, specifically to force a static universe. When Hubble's observations proved the universe was expanding, Einstein called this his greatest blunder. To truly grasp what this means, we need to think about what space and time are at a fundamental level. Before Einstein, space was thought of as an absolute, unchanging arena, like a stage on which events played out. Time was thought of as a universal clock, ticking forward at the same rate everywhere. Newton's laws of motion and gravity assumed this framework. Einstein shattered these assumptions. In special relativity, he showed that time is relative. Moving clocks tick slower than stationary ones. Objects moving near the speed of light contract in the direction of motion. Events that appear simultaneous to one observer occur at different times for another observer moving at a different velocity. Space and time are not absolute but depend on the motion of the observer. General relativity extended this to gravity and acceleration. Einstein realized that someone in free fall experiences no gravity. An astronaut in orbit is weightless, not because there is no gravity, but because they are falling freely through the gravitational field. Conversely, someone standing on Earth's surface feels weight not because gravity is pulling them down, but because the ground is pushing them up, accelerating them through curved space-time. This led Einstein to a radical conclusion. Gravity is not a force at all, at least not in the conventional sense. It is the curvature of space-time. Massive objects bend the space-time around them, and other objects follow the curved paths through that bent space-time. What we experience as gravitational attraction is actually objects following the natural geodesics, the straightest possible paths through curved space-time. The mathematics that describes this is tensor calculus, a branch of mathematics that was still being developed when Einstein worked on general relativity. The field equations of general relativity relate the curvature of space-time, described by the Riemann curvature tensor, to the distribution of matter and energy, described by the stress-energy tensor. Solving these equations for a given distribution of matter tells you how space-time curves, and knowing the curvature tells you how matter moves. For the universe as a whole, cosmologists use a simplified version of Einstein's equations based on two assumptions: homogeneity and isotropy. Homogeneity means the universe looks the same at every location when averaged over sufficiently large scales. Isotropy means it looks the same in every direction. These assumptions are observationally justified. The cosmic microwave background is uniform to 1 part in 100,000 across the entire sky, and galaxy surveys show that matter is distributed uniformly when you average over scales of hundreds of millions of light years. With these assumptions, the equations simplify enormously. The result is the Friedmann equations, named after Alexander Friedmann, who derived them in 1922. These equations describe how the size of the universe changes over time based on its energy content. They show that a universe filled with matter and radiation cannot be static. It must either expand or contract. The Friedmann equations contain a parameter called the scale factor, usually denoted by the letter A. The scale factor describes how distances in the universe change over time. If the scale factor doubles, then the distance between any two unbound objects doubles. The expansion of the universe is literally the increase of this scale factor over time. Critically, the scale factor applies to space itself, not to objects moving through space. When we say the universe is expanding, we mean the scale factor is increasing. Distances are growing not because objects are moving apart through static space, but because the space between them is being stretched. This stretching happens everywhere at once. There is no center to the expansion. Every observer, regardless of where they are located, will see distant galaxies receding from them in proportion to their distance. This is what the balloon analogy tries to capture. No point on the balloon's surface is special, and every point sees every other point moving away as the balloon inflates. but the cosmological constant would return in an unexpected way decades later. For now, what matters is understanding that the expansion of the universe is an expansion of spacetime itself. When we say space is getting bigger, we mean that the distances between objects that are not bound together by gravity are increasing because the spacetime that contains them is stretching. This stretching is uniform and isotropic, meaning it happens at the same rate in all directions and at all locations throughout the universe. There is no center to the expansion, no special point from which everything else is receding. Every observer, no matter where they are located, will see distant galaxies receding from them according to Hubble's law. This is because the expansion is a property of spacetime itself, not a motion through spacetime. One way to think about this: imagine you are an ant crawling on the surface of an expanding balloon. As the balloon inflates, the distance between you and other ants on the surface increases, but there is no special point on the balloon surface that is the center of this expansion. Every ant sees every other ant moving away, and from each ant's perspective it might seem like they are at the center. But in reality, there is no center on the two-dimensional surface. The center of the balloon exists in a third dimension that the ants do not have access to. Similarly, if the universe has a center to its expansion, it would exist in a higher dimension that we do not have access to. From within the three-dimensional space we inhabit, there is no center. This brings us to a profound realization. When we ask, what is the universe expanding into? We're implicitly assuming that space-time is embedded in some larger space, the way the balloon surface is embedded in three-dimensional room. But general relativity tells us that space-time is not embedded in anything. It is the fundamental reality. There is no larger container, no external space, no outside. Space-time is all there is, and it is expanding, but not into anything external, to itself. The expansion of space-time means that distances between distant objects grow larger over time, not because those objects are moving through space, but because the space between them is literally growing. New space is continuously coming into existence. This does not violate any conservation laws because space itself is not a substance that can be created or destroyed in the conventional sense. It is the arena in which substances exist, and that arena can change its properties, including its size. Understanding space-time as a four-dimensional dynamic curved structure is essential to grasping what cosmic expansion really means. It is not an explosion into pre-existing space. It is not galaxies flying apart through a static void. It is the fundamental fabric of reality itself changing, evolving, stretching in accordance with the laws of physics. This stretching has been happening for approximately 13.8 billion years, ever since the moment we call the Big Bang, and it continues today, carrying galaxies farther and farther apart as eons pass. And yet, despite this expansion, despite the fact that space is getting bigger, there is still no outside for it to expand into. The universe is not growing into anything, it is simply growing. This is where language begins to fail us completely, where visualization becomes impossible, and where we must rely on mathematical descriptions to grasp what is truly happening. But even without being able to picture it perfectly, we can understand the principle. The universe is everything, and everything is getting bigger, and that is all we need to know to dispense with the question of what it is expanding into. Scientists and educators often use the balloon analogy to explain cosmic expansion, and for good reason. It captures several crucial aspects of how the universe behaves, but it is important to understand both what this analogy reveals and where it catastrophically breaks down. Imagine taking a deflated balloon and drawing dots on its surface with a marker. Each dot represents a galaxy. Now inflate the balloon. As the balloon expands, several things happen that mirror the actual universe. First, every dot moves away from every other dot. There is no privileged center. From any dot's perspective, all the other dots are receding. Second, dots that are farther apart separate faster than dots that are close together. This matches Hubble's law. Third, the expansion happens not because the dots themselves are moving across the balloon's surface, but because the surface itself is stretching. These are powerful insights. The balloon analogy helps people grasp that cosmic expansion is about space itself growing, not objects racing through static space. It shows why there is no center to the expansion from the perspective of observers within the system. It demonstrates the relationship between distance and recession velocity. But here is where the analogy begins to fail, and fail dramatically. The balloon exists in three-dimensional space. Its two-dimensional surface expands by pushing outward into the third dimension. We can see the balloon from the outside. We can watch it grow larger within the room that contains it. We understand that the surface is stretching because the interior volume of the balloon is increasing, displacing the air around it. All of this makes perfect intuitive sense. The universe does none of this. Our universe is three-dimensional, or more precisely four-dimensional if we include time. It is not embedded in a higher dimensional space that we can observe from the outside. There is no fifth dimension that the universe is expanding into, at least not in any way we can detect or interact with. The expansion of the universe is intrinsic, happening from within, without reference to any external space. When people see the balloon analogy, they naturally extrapolate. If the balloon's surface expands by pushing into three-dimensional space, then surely the universe's three-dimensional space expands by pushing into four-dimensional space, or five-dimensional space, or some higher dimensional realm. This seems logical, but it is wrong. General relativity describes the universe as a four-dimensional space-time manifold that is not embedded in anything higher. Its expansion is a change in its own intrinsic geometry, not a growth into external dimensions. Another limitation of the balloon analogy, it suggests the universe has a finite size. After all, a balloon's surface has a finite area. You could, in principle, walk around the entire surface and return to your starting point. If the universe is like the balloon's surface, does that mean the universe is also finite? That you could travel in one direction and eventually loop back to where you started? Maybe, but maybe not. The balloon analogy specifically represents a closed universe with positive curvature, one of three possible geometries the universe could have. Observations suggest our universe is actually flat, or very nearly so, with curvature close to zero. A flat universe could be infinite in extent, or it could be finite with a different topology than a sphere. The balloon analogy does not capture these possibilities. There is also the problem of the balloon's center. The balloon has a literal center in three-dimensional space, located inside the balloon where the air is. This center is not on the surface where the dots are drawn, but it exists nonetheless. People seeing this analogy sometimes conclude that the universe must also have a center, perhaps in some higher dimension we cannot perceive, but this is not required by the physics. The universe might simply have no center at all, in any dimension. Moreover, the balloon is expanding because someone is blowing air into it, or because air inside it is heating up and increasing in pressure. There is a physical mechanism driving the expansion that we can point to and understand. The universe's expansion is not driven by anything pushing from outside or by any conventional pressure. In the early universe, it was driven by the inherent properties of space-time emerging from the Big Bang. Today, it is driven by something we call dark energy, but we do not fully understand what dark energy is or why it causes space to expand faster over time. Finally, the balloon analogy is two-dimensional, representing three-dimensional reality. Ants crawling on the balloon surface can only move in two dimensions. They cannot perceive the third dimension into which the balloon expands. When we try to extend this to the universe, we have to imagine ourselves as three-dimensional beings embedded in three-dimensional space, unable to perceive the higher dimensions into which the universe might be expanding. But this creates more confusion than clarity, because it tempts us to believe those higher dimensions must exist, when in fact, our best current physics suggests they do not. Despite these limitations, the balloon analogy remains useful for building initial intuition. It helps people break free from the idea that the Big Bang was an explosion in pre-existing space. It shows how recession velocity can be distance-dependent without requiring a center. It illustrates that expansion is a property of space itself. These are valuable insights, and the analogy deserves credit for communicating them effectively, but it must be abandoned or heavily modified when we push deeper into cosmology. The universe is not a balloon. It is not a surface embedded in higher dimensions. It is not expanding into anything external. These truths are mathematically rigorous but nearly impossible to visualize, which is why analogies like the balloon are both indispensable and dangerous. They provide a stepping stone toward understanding, but we must be willing to discard them when they no longer serve us. Physicists sometimes say that if you can visualize it, you are probably thinking about it wrong. This is especially true for cosmic expansion. The moment you form a clear mental picture of the universe as a sphere growing larger within some containing space, you have imported assumptions that do not match reality. The universe does not look like anything from the outside because there is no outside. It does not have an edge or a boundary or a surface beyond which something else exists. It simply is, and it is getting bigger, and that is the full extent of the truth we can state clearly. Learning to think about the universe in these abstract terms, to grasp concepts without mental images, is one of the hardest cognitive challenges in all of science. But it is also one of the most rewarding. It shows that reality transcends our intuitions and our visualizations. It reveals that mathematics can guide us to truths our senses and our spatial reasoning could never reach on their own. And it proves that humans, despite the limitations of our evolved brains, can genuinely understand the cosmos, even when we cannot picture it clearly. One of the deepest questions in cosmology is whether the universe is infinite or finite in extent. The answer profoundly affects how we think about cosmic expansion and what it means for space to grow larger. If the universe is infinite, then it has always been infinite. Even immediately after the Big Bang, when all the space we can currently observe was compressed into a tiny volume, the totality of space was still infinite. As an infinite universe expands, it remains infinite, but the distances between any 2 points grow larger. Every finite region of space grows in size, but the whole of space was and always will be infinite. This might seem paradoxical. How can something infinite get bigger? But mathematically, it is entirely coherent. Imagine an infinite line of numbers: 3, 2, 1, 0, 1, 2, 3. Now imagine stretching this line so that every number is twice as far from 0 as before. 6, 4, 2, 0, 2, 4, 6. The line is still infinite, but the spacing between numbers has doubled. In the same way, an infinite universe can expand by increasing the distances between all points while remaining infinite in total extent. If the universe is infinite, then the question, what is it expanding into, becomes even more clearly nonsensical. An infinite space is not surrounded by anything. It has no edge, no boundary, no outside. It is already everything. When it expands, there is no external space required because the expansion is about distances within the space changing, not about the space pushing into some external region. On the other hand, the universe might be finite. A finite universe has a total volume that, while enormous, is not infinite. This might seem like it requires an edge, a place where space ends and something else begins. But remarkably, a finite universe does not need an edge. It can be finite and yet unbounded, with no boundary or edge anywhere. How is this possible? Through topology. The shape of space can be such that travelling in a straight line in any direction would eventually bring you back to your starting point, without ever encountering an edge. Think of the surface of a sphere. It has a finite area but no edge. An ant crawling on a sphere could walk forever and never fall off or reach a boundary. The two-dimensional surface is finite but unbounded. The same can be true in 3 dimensions, though it is impossible for humans to visualize directly. One possibility is a 3-dimensional sphere, a hypersphere, which has a finite volume but no boundary. If the universe has this shape, you could travel in a straight line in any direction, and given enough time, you would eventually return to where you started, having circumnavigated the universe. But you would never encounter an edge or a wall. Another possibility is a 3-dimensional torus, analogous to the surface of a donut but extended to 3 dimensions. In such a universe, space wraps around on itself in multiple directions. Travel far enough in any direction, and you loop back. This is called a multiply connected space, and it is finite without requiring any boundary. The geometry of the universe, its overall curvature, determines whether it is infinite or finite. General relativity allows for 3 basic geometries. A positively curved universe, like the surface of a sphere, is necessarily finite. A flat universe, with 0 curvature, can be either infinite or finite depending on its topology. A negatively curved universe, like a saddle shape, is generally infinite, though certain exotic topologies could make it finite. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, have allowed cosmologists to measure the curvature of the universe with remarkable precision. The results show that the universe is flat, or extraordinarily close to flat, with curvature differing from 0 by less than 0.4%. This means the universe could be infinite, or it could be finite with a flat but multiply connected topology, like a three-dimensional torus. If the universe is flat and simply connected, meaning it does not wrap around on itself, then it is infinite in extent. Space goes on forever in all directions, containing an infinite number of galaxies, stars, and planets. In such a universe, every possible arrangement of matter that can exist does exist, infinitely many times over, in regions far beyond our observable horizon. If the universe is flat but multiply connected, it could be finite. Light could travel across the entire universe and loop back, potentially allowing us to see multiple images of the same galaxy in different directions. Cosmologists have searched for such repeated patterns in the cosmic microwave background and in the distribution of galaxies, but so far they have found no evidence for them. This does not rule out a finite universe. It merely means that if the universe is finite, it is larger than the observable universe, and we cannot detect its finite extent from our vantage point. Whether the universe is infinite or finite has implications for what expansion means. In an infinite universe, expansion is about the distances between structures growing larger, with no overall boundary expanding into anything. In a finite universe, the total volume increases, but there is still no external space that this volume expands into. In both cases, the expansion is intrinsic to the universe itself. The question also affects philosophical considerations. An infinite universe is humbling in a particular way. It means that everything that can happen does happen somewhere infinitely many times. Every variation, every possibility, every conceivable arrangement of matter exists. We are not unique. There are infinite versions of you, scattered across an infinite cosmos, living lives identical to yours or subtly different or wildly divergent. A finite universe is humbling differently. It means there is a limit to what exists, a totality that, while vast, is comprehensible in principle. The universe contains a finite amount of matter and energy, a finite number of stars and galaxies, a finite number of possible states. Everything is rare and precious because there are only so many configurations that can exist. Current evidence does not definitively answer whether the universe is infinite or finite. The measurements are consistent with both possibilities. It is conceivable that future observations might reveal subtle signs of a finite topology, patterns in the cosmic microwave background, or the distribution of galaxies that betray a multiply connected space. Or we might accumulate more and more evidence that the universe is flat and simply connected, strengthening the case for infinity. Either way, the expansion is real. Whether the universe is infinite or finite, space is getting bigger. Distances between galaxy clusters are growing. The cosmos is evolving, changing, stretching, in accordance with the equations of general relativity, and in either case there is no outside. An infinite universe has no exterior because it is already everything. A finite universe has no exterior because its boundary would be a contradiction. If something existed beyond the boundary, that something would be part of the universe by definition. This is why the question, what is the universe expanding into, remains so beautifully, frustratingly unanswerable. It presupposes an outside that does not exist. It asks for a containing space when the universe is the totality of space itself. The universe is not expanding into anything because there is no anything for it to expand into. It is expanding in the only way that makes sense given the structure of spacetime, by becoming larger within itself. To truly understand cosmic expansion, we must travel back to the beginning, to the first moments after the Big Bang, when the universe underwent the most extraordinary transformation in its history. Approximately 13.8 billion years ago, the universe emerged from a state of unimaginable density and temperature. In the first fraction of a second, it was smaller than an atom, hotter than anything we can directly comprehend, and governed by physics we are still struggling to understand. Then, in the tiniest sliver of time, something remarkable happened. The universe inflated. Between approximately 10⁻⁵ and 10⁻33 seconds after the Big Bang, the universe underwent a period of exponential expansion, known as cosmic inflation. During this brief instant, space expanded by a factor of at least 10^26, possibly far more. Regions that were once so close together that they could interact via light signals were were suddenly separated by distances so vast that light could never traverse them. This is not a metaphor or an exaggeration. Inflation is the most rapid expansion event in cosmic history, dwarfing anything that has happened since. The universe literally doubled in size every 10^37 seconds during inflation. Doubled again and again and again. At least 90 times, possibly many more. Within a fraction of a second too small for the human mind to truly grasp, the universe went from smaller than a subatomic particle to larger than a golf ball, and possibly much larger. Why did this happen? The answer involves quantum fields and the physics of the very early universe, areas where our understanding is still incomplete. The leading theory is that inflation was driven by a special kind of field called the inflating field, which filled all of space with a peculiar form of energy. This energy had negative pressure, meaning it pushed outward rather than pulling inward like gravity. The negative pressure caused space itself to expand exponentially, faster and faster, until the inflating field decayed and transferred its energy into the hot, dense soup of particles we associate with the early universe. Inflation solves several critical problems that plagued earlier models of the Big Bang. One is the horizon problem. When we look at the cosmic microwave background radiation, we see that it has nearly the same temperature in all directions, differing by only 1 part in 100,000. This uniformity suggests that different regions of the early universe were in thermal equilibrium, meaning they had exchanged energy and come to the same temperature. But according to standard Big Bang cosmology without inflation, regions on opposite sides of the sky were never close enough to exchange light signals, let alone come to equilibrium. How could they have the same temperature if they were never in contact? Inflation solves this. Before inflation, the entire observable universe was compressed into a region small enough that all parts could interact and reach the same temperature. Then inflation expanded this tiny uniform patch to cosmological scales, preserving the uniformity. Regions that are now on opposite sides of the observable universe were once next to each other, which is why they have the same temperature today. Another problem is flatness. Observations show the universe is flat to within a fraction of a percent, but any deviation from perfect flatness grows rapidly over time as the universe expands. To be as flat as we observe today, the early universe must have been flat to within 1 part in 1060, an absurdly precise value. Why would the universe start with such special initial conditions? Inflation answers this too. The exponential expansion during inflation stretches space so dramatically that any initial curvature is smoothed out. Just as inflating a balloon makes its surface appear flatter and flatter, inflation made the universe flat regardless of what curvature it started with. After inflating by a factor of 1026 or more, even a highly curved universe would appear perfectly flat. Inflation also explains the origin of structure in the universe. Quantum mechanics tells us that on the smallest scales, fields fluctuate, randomly due to the uncertainty principle. During inflation, these tiny quantum fluctuations were stretched to macroscopic and even cosmological scales. The fluctuations became frozen into the fabric of space itself, creating slight variations in density from one region to another. After inflation ended, these density variations acted as seeds for structure formation. Regions slightly denser than average attracted more matter, eventually collapsing under gravity to form the first stars, galaxies and galaxy clusters. This is remarkable. The largest structures in the universe, superclusters of galaxies spanning hundreds of millions of light-years, originated as quantum fluctuations smaller than an atom. Inflation took something microscopic and made it cosmic. We can observe the imprint of these primordial fluctuations today in the cosmic microwave background radiation and in the distribution of galaxies across the sky. They match the predictions of inflation theory with stunning precision. Inflation also gives us a framework for understanding what the universe was expanding into during those first moments. The answer, as always, is nothing. Inflation was not an explosion into pre-existing space. It was the rapid growth of space itself. The volume of the universe increased exponentially, but there was no external container that this volume filled. Space expanded from within, according to the equations of general relativity modified to include the inflating field. One of the strangest implications of inflation is that it might still be happening. Not in our region of the universe, where inflation ended 13.8 billion years ago, and was replaced by the slower expansion we observe today. But in other regions, far beyond our cosmic horizon, inflation may continue. This is the idea of eternal inflation. If inflation once started is difficult to stop completely, then it might persist in some regions while ending in others. Our universe would be just one bubble in an eternally inflating cosmos, one of countless regions where inflation ended and a hot Big Bang began. In this picture, what we call the universe, everything we can observe is just a tiny pocket within a much larger inflating structure. Other pockets, other universes, would exist beyond our horizon, each with potentially different properties, different laws of physics, different constants of nature. This multiverse scenario is speculative and controversial, but it emerges naturally from the mathematics of inflation. Whether or not eternal inflation is real, standard inflation remains one of the cornerstones of modern cosmology. It explains why the universe is flat, why it is uniform, and where the seeds of structure came from. It shows that the expansion we observe today is just the latest chapter in a story that began with the most dramatic expansion event imaginable. And throughout it all, the universe was not expanding into anything. During inflation, just as today, space grew larger, without needing external space to grow into. The universe was everything, and everything was growing, and that was sufficient. Human language evolved to describe objects in space, not space itself. This creates a profound difficulty when we try to discuss the universe as a whole. Nearly every word we use to describe expansion implicitly assumes a spatial framework larger than the thing expanding. We say an object expands into something, or that it fills a volume, or that it pushes outward against boundaries. All of these phrases presuppose that there is something beyond the expanding object. For the universe, this presupposition is wrong. There is nothing beyond the universe because beyond is a spatial concept, and the universe is the totality of space. Asking what is outside the universe is like asking what is north of the North Pole. The question is grammatically correct but conceptually incoherent. It applies a relational term in a context where that relation cannot exist. To understand why, we need to think carefully about what outside means. Normally, when we say something is outside an object, we mean it occupies a different region of space than that object. The chair is outside the room. The solar system is outside our galaxy's central core. Mars is outside Earth's atmosphere. In each case, outside refers to a spatial separation within a common framework of space that contains both the object and the region external to it. But the universe is not an object within a framework of space. The universe is the framework. It is space itself, along with everything space contains. There is no larger spatial framework that could contain both the universe and an external region. The concepts of inside and outside lose their meaning when applied to the totality of space. Some people try to escape this by invoking higher dimensions. Perhaps the universe is a three-dimensional object embedded in four-dimensional space, or five-dimensional space, or some even higher dimensional realm. In that case, outside would refer to regions of the higher dimensional space that are not part of our three-dimensional universe. This is mathematically possible, and certain theories in physics, such as string theory, do propose extra dimensions. But there is no evidence that these extra dimensions exist in a way that provides an outside to our universe. Moreover, even if extra dimensions exist, the question, what is the universe expanding into, would not necessarily have a clear answer. The expansion of our three-dimensional space could occur entirely within our three-dimensional slice of the higher dimensional space, with no growth into the extra dimensions. Or the expansion could be intrinsic to the full higher dimensional space-time, in which case we are back to asking what that higher dimensional space expands into, and we have not solved the problem, only deferred it. The cleanest answer, and the one that best matches our current understanding of physics, is that the universe is not embedded in any higher dimensional space. It is the fundamental reality. Space is not contained within something, it is the container itself, and that container can change its properties, including its size, without needing to be placed within a larger container. This is where the failure of visualization becomes most acute. We cannot help but picture the universe as a thing, an object with boundaries, existing within a larger context. But this mental image is wrong. The universe is not a thing within something else. It is the only thing, the totality of existence, and it is evolving according to the laws of physics. Another way to think about this: the universe is a closed system. In thermodynamics, a closed system is one that does not exchange matter or energy with its surroundings. The universe is the ultimate closed system because it has no surroundings. There is nothing outside it to exchange anything with. All of the matter, energy, space, and time that exist are contained within the universe itself. When physicists say the universe is expanding, they mean that the distances between objects not bound by gravity are increasing over time. This is an observational fact, measured through the redshift of light from distant galaxies. The expansion can be described mathematically using general relativity, and it does not require any external space. The equations describe how the geometry of spacetime evolves based on its current state and the matter and energy it contains. External space is simply not part of the description. This might feel unsatisfying. Our brains want to know where the new space comes from. If space is growing larger, does that not mean new space is being created? And if so, where was it before? These questions presuppose that space is a substance that can be created, stored, and retrieved. But space is not a substance. It is a relational structure, a framework that describes the distances between objects and the geometry of how those distances change. When space expands, we're not creating new space stuff. We're changing the distances, the geometry. Imagine a grid of coordinates marking positions in space. If the universe expands, the distances between coordinate points increase. But we have not created new coordinate points. We have simply rescaled the distances. The grid now describes a larger region, but we did not have to import that region from somewhere else. We just changed the metric, the way we measure distances. In general relativity, this is made precise through the metric tensor, a mathematical object that encodes how distances are measured in spacetime. The expansion of the universe corresponds to the metric tensor evolving over time, with distances between points growing larger. This is a change in the intrinsic geometry of spacetime, not a growth into external space. So when we ask, what is the universe expanding into, we're asking a question that assumes a conceptual framework that does not apply. The universe is not the kind of thing that expands into something else. It is the kind of thing that expands intrinsically, from within, without reference to anything external. This is difficult to accept emotionally, because it violates our intuitions, but it is what the mathematics tells us, and it is confirmed by every observation we have made. One of the most profound implications of cosmic expansion is the existence of cosmic horizons, boundaries beyond which we cannot see, not because of any limitation in our telescopes, but because of the fundamental structure of spacetime itself. Light travels at a finite speed, approximately 300,000 kilometers per second. This is not just fast, it is the cosmic speed limit, the maximum velocity at which any information can travel through space. Nothing with mass can reach this speed, and even massless particles like photons travel at exactly this speed, no faster, no slower. This fundamental constant shapes everything about how we observe the universe. Because light travels at a finite speed, when we look at distant objects, we see them not as they are now, but as they were in the past. When we observe a galaxy 1 billion light-years away, we see it as it existed 1 billion years ago, because that is how long the light has taken to reach us. The light that enters our telescopes today left that galaxy when the universe was significantly younger, when stars were forming at different rates, when the galaxy itself might have had a different shape and structure. This creates a horizon. The universe is approximately 13.8 billion years old. Light from objects more than 13.8 billion light-years away has not had time to reach us yet. So there is a maximum distance we can observe, a cosmic horizon beyond which we cannot see. Actually, the situation is more complicated because the universe is expanding. During the time light has been travelling toward us from distant galaxies, those galaxies have been moving farther away due to the expansion of space. This means the actual distance to a galaxy whose light has taken 13.8 billion years to reach us is much greater than 13.8 billion light-years. To understand this, imagine a photon emitted from a galaxy shortly after the Big Bang, travelling toward what will eventually become the Milky Way. As this photon journeys through space, space itself is expanding. The distance between the photon and its destination is growing, even as the photon covers ground. It is like running on a treadmill that is gradually speeding up. The photon makes progress, but its destination keeps receding. Despite this challenge, some photons do eventually reach us. The ones we observe today from the most distant galaxies have been travelling for almost the entire age of the universe. But during their journey, the galaxies that emitted them have been carried away by expansion. Accounting for this expansion, cosmologists calculate that the radius of the observable universe, the distance to the most distant objects we can theoretically see, is approximately 46 billion light-years. Think about what this means. We live at the centre of a sphere 92 billion light-years in diameter. Everything within this sphere is, in principle, observable. Light from any object in this region has had time to reach us since the Big Bang. Beyond this sphere lies the unobservable universe, regions from which light has not yet arrived. But this is just the observable universe, the region from which light has had time to reach us. The total universe could be much larger, possibly infinite. If the universe is infinite, then the observable universe is just a tiny bubble within an infinite expanse. Most of the universe is beyond our horizon, and we can never observe it directly. Consider the implications of this. Right now, at this very moment, there are galaxies beyond our cosmic horizon. These galaxies exist. They contain stars and planets. Some of those planets might harbour life, but we can never see them. Not now, not ever, because the light they emit has not had time to reach us. They are as real as the galaxies we can observe, governed by the same laws of physics, made of the same matter and energy. Yet they are forever hidden from view. The expansion of the universe creates an even more stringent limit, because space itself is expanding, and the expansion rate is the same per unit distance. Objects that are sufficiently far away are receding from us faster than light can travel. This creates a cosmic event horizon, a boundary beyond which light emitted today will never reach us, no matter how long we wait. For objects beyond the cosmic event horizon, the space between us and them is expanding so rapidly that even if they emit light in our direction, that light will never cross the intervening distance. The expansion carries the light away faster than it can approach us. These objects are permanently beyond our reach, causally disconnected from us for all future time. The cosmic event horizon is not the same as the observable universe horizon. The observable universe represents the limit of what we can see based on light that has already reached us. The cosmic event horizon represents the limit of what we could ever see, even if we waited indefinitely. The event horizon is closer, with a current radius of approximately 16 billion light-years, significantly smaller than the observable universe. This means that some galaxies we can see now, whose light was emitted billions of years ago and has reached us, are already beyond our event horizon. We will never see what they look like in the present. The light they are emitting now will never reach us because they are receding too fast. We can observe their past, but their present and future are forever hidden. Over time, more and more galaxies will cross our event horizon. In the distant future, assuming the expansion continues to accelerate as current evidence suggests, observers in our galaxy will see a much emptier universe. Most of the galaxies we can see today will have receded beyond the horizon. Their light will be redshifted into invisibility. Eventually, only the galaxies in our local group, bound to us by gravity and therefore not receding, will be visible. The rest of the cosmos will be dark. This future scenario has profound implications. Imagine a civilization arising in our galaxy 10 billion years from now, when the sun has long since died and been replaced by new generations of stars. What will these future beings observe when they look out at the cosmos? They will see the Milky Way, or whatever it has become after merging with Andromeda and other local galaxies. They will see a few dozen nearby galaxies in the local group, but beyond that, darkness. The billions of galaxies we observe today will have receded beyond the event horizon. The cosmic microwave background radiation, the faint afterglow of the Big Bang, will be so redshifted that it might be undetectable with any conceivable technology. These future beings might conclude they live in a static, solitary universe containing only a few galaxies, unaware of the vast cosmos that existed beyond their horizon. They might never discover the Big Bang because the evidence for it will have faded away. They might never learn that the universe is expanding because everything they can observe will be gravitationally bound and not participating in the expansion. In a sense, we are living in a golden age of cosmology. We can still see enough of the universe to piece together its history, and understand its evolution. We can observe the cosmic microwave background and trace it back to the Big Bang. We can measure the expansion and discover its acceleration. Future civilizations might not have these opportunities. The expanding universe will have carried the evidence away. This illustrates an important point. What we can observe is not necessarily all that exists. The observable universe is a subset of the total universe, possibly a tiny subset. When we talk about the universe expanding, we are talking about the expansion of all of space, not just the part we can see. The regions beyond our horizon are expanding too, carrying structures and galaxies farther and farther apart, even though we can never observe them directly. The existence of cosmic horizons also reinforces why the question, "What is the universe expanding into?" is misguided. Even if there were an external space for the universe to expand into, we could never observe it because it would be beyond our horizon. From our perspective, the observable universe is all we can ever know, and within that observable universe, all we see is expansion described perfectly by general relativity without requiring any external space. Horizons in cosmology are not physical barriers, they are simply limits on how far we can see and how far we can interact with the cosmos. Light from beyond the horizon has not reached us yet, or will never reach us, but the regions beyond the horizon are made of the same space, the same matter and energy, governed by the same laws of physics. They are part of the same universe, just causally disconnected from us. This brings up a philosophical question. If parts of the universe are forever beyond our observation, are they real? Most scientists would say yes. The laws of physics apply everywhere, not just where we can see. The universe does not care whether we are watching. Regions beyond our horizon exist just as surely as regions within it. But there is no empirical way to verify this claim because, by definition, we cannot observe those regions. We must rely on theoretical reasoning and the principle that the laws of physics are universal. If the laws work here, in the observable universe, then they should work everywhere. The expansion should continue beyond our horizon. Galaxies should form and evolve, stars should shine and planets should orbit. All of this happens beyond our view, part of a larger cosmic story we can only partially witness. The expansion of the universe, combined with the finite speed of light, creates a cosmos where most of existence is invisible to us. We live in a small bubble of space within a potentially infinite expanse, and that bubble is surrounded by horizons we can never cross. Yet the expansion continues everywhere, in the regions we can see and the regions we cannot, driven by the same physics, unfolding according to the same equations, indifferent to our ability to observe it. And remarkably, all of this expansion, both within and beyond our horizon, requires no external space. The universe is not pushing into anything. It is simply getting bigger, distances growing, space stretching, in accordance with the geometry of spacetime itself. The horizons limit our observation but do not change the fundamental nature of what is happening. The universe expands into nothing because there is nothing to expand into, and this remains true whether we can observe that expansion or not. For decades after Hubble's discovery, cosmologists assumed the expansion of the universe was slowing down. Gravity, after all, is an attractive force. All the matter in the universe should be pulling on all the other matter, acting like a brake on the expansion. The question was whether gravity was strong enough to eventually halt the expansion and reverse it, causing the universe to collapse back into a big crunch, or whether the expansion would continue forever, gradually slowing but never stopping. In 1998, two teams of astronomers studying distant supernovae made a discovery that stunned the scientific community. The expansion of the universe was not slowing down, it was speeding up. The universe was expanding faster today than it was billions of years ago, and the acceleration appeared to be increasing. This was utterly unexpected. There was no known mechanism that could cause cosmic acceleration. Gravity pulls, it does not push. Yet the observations were clear. Distant supernovae were fainter than they should be if the universe were decelerating, indicating they were farther away than expected. Space was expanding faster than models predicted. To explain this, cosmologists invoked a concept that Einstein had introduced and then abandoned: the cosmological constant. In his original formulation of general relativity, Einstein included a term denoted by the Greek letter lambda that represented a repulsive force permeating all of space. He added this term to force his equations to produce a static universe, which he believed was the correct model. When Hubble discovered the universe was expanding, Einstein called the cosmological constant his greatest blunder and removed it from his equations. But the cosmological constant, or something very much like it, has made a dramatic comeback. The observed acceleration of the universe can be explained if space itself contains a form of energy that has negative pressure. This energy, called dark energy, does not clump or cluster like matter. It is distributed uniformly throughout space, and it has the bizarre property of pushing space apart rather than pulling it together. Dark energy is the dominant component of the universe, making up approximately 68% of the total energy density. Dark matter, the invisible substance that provides the gravitational scaffolding for galaxies and clusters, accounts for about 27%. Ordinary matter, the atoms that make up stars, planets, and people, accounts for a mere 5%. We are a tiny fraction of the cosmos, surrounded by forms of matter and energy we do not fully understand. The nature of dark energy is one of the greatest mysteries in physics. We know it exists because we observe its effects, the accelerating expansion of the universe, but we do not know what it is. The simplest explanation is that dark energy is the cosmological constant, a property of space itself. Empty space, according to quantum field theory, is not truly empty. It seethes with virtual particles that pop in and out of existence, contributing a baseline energy density to the vacuum. This vacuum energy could be the cosmological constant. However, there is a problem. When physicists calculate the expected value of vacuum energy from quantum field theory, they get a number that is 10 to 120 times larger than the observed value of dark energy. This is the worst prediction in the history of physics, off by 120 orders of magnitude. Either our understanding of quantum field theory is profoundly incomplete, or some mechanism we do not understand cancels out almost all the vacuum energy, leaving only the tiny amount we observe. Alternatively, dark energy might not be a constant. It could be a dynamic field that changes over time, called quintessence. In this scenario, the density of dark energy could vary, increasing or decreasing as the universe evolves. Quintessence would have different observational signatures than a cosmological constant, and future observations might be able to distinguish between them. Regardless of what dark energy is, its effects on cosmic expansion are dramatic. In the early universe, matter and radiation dominated. Their gravitational pull slowed the expansion, but as the universe grew larger, the density of matter and radiation decreased, while the density of dark energy remained constant. About 5 billion years ago, dark energy became dominant, and the expansion started to accelerate. The acceleration will continue indefinitely if dark energy remains constant or grows stronger. This has profound implications for the future of the universe. The expansion will carry galaxies farther and farther apart. Clusters of galaxies not bound to each other by gravity will lose contact. Eventually, our observable universe will consist only of our local group of galaxies, gravitationally bound together while everything else recedes beyond the cosmic horizon. The cosmos will become darker, emptier, colder. Stars will exhaust their fuel. No new stars will form because the gas needed for star formation will be too dispersed. The universe will enter an era dominated by dead remnants, white dwarfs, neutron stars, black holes. Over timescales of 10 or 100 years or more, even black holes will evaporate through Hawking radiation. The universe will approach a state of maximum entropy, a cold, dark, nearly empty expanse where nothing changes and nothing happens. This is the big freeze, the ultimate fate of an accelerating universe, but this is trillions of years in the future. For now, the acceleration of expansion tells us something crucial about the universe we inhabit. It is not just expanding, it is expanding faster over time, driven by a mysterious energy we do not understand. And crucially, this acceleration does not require the universe to expand into anything external. Dark energy is a property of space itself, and as space expands, the total amount of dark energy increases because there is more space. This creates a feedback loop. More dark energy accelerates expansion, which creates more space, which contains more dark energy, accelerating expansion further. All of this happens within the universe. The expansion is intrinsic, driven by the energy and curvature of spacetime itself, governed by the equations of general relativity. There is no external space needed, no outside into which the universe grows. The acceleration makes the expansion more dramatic, more rapid, but it does not change the fundamental nature of what expansion means: space getting bigger from within, without reference to anything external. The expansion of the universe into nothingness is not just a scientific fact, it is a philosophical earthquake. It challenges our most basic intuitions about reality, existence, and the limits of human understanding. For millennia, humans have constructed cosmologies that place them, if not at the center of the universe, at least within a comprehensible framework. The Earth was the center of the cosmos, then the Sun was the center of the solar system, then the Milky Way was one galaxy among billions. Each step decentered humanity, but each step still preserved the idea that we existed within a container, a larger structure that gave context to our existence. The modern understanding of cosmic expansion obliterates even this residual comfort. The universe is not a container. It is not a thing within a framework. It is the framework, and the framework itself is changing, evolving, expanding in ways that defy visualization and intuition. We are not just decentered. We are adrift in a cosmos that does not have a center, does not have edges, and does not exist within anything larger than itself. This is profoundly disorienting. Humans need context. We orient ourselves by reference points, by boundaries, by knowing where we are in relation to something else. But the universe provides no such reference points. It is everything, and it is expanding, and there is nothing outside it to compare it to. We are embedded within the only thing that exists, unable to step outside it, unable to view it from an external perspective. This limitation is not just practical but fundamental. We cannot, even in principle, observe the universe from the outside because there is no outside. We are inside observers, bound by the same physical laws as everything else, observing a cosmos that contains us. This creates a kind of existential vertigo. We are simultaneously insignificant specks in an incomprehensibly vast cosmos, and the only known observers of that cosmos, the universe's way of becoming aware of itself. The expansion of the universe also raises questions about the nature of space and time. If space is expanding, what is it made of? What does it mean for something to grow larger if that something is not a substance but a relational structure? These questions push at the boundaries of our conceptual frameworks. We have words like space and expansion, but the phenomena they describe are so far removed from everyday experience that the words might be misleading more than illuminating. Philosophically, the expansion of the universe reveals the limits of language and thought. We evolved to survive in a particular niche, navigating three-dimensional space at speeds far slower than light, interacting with objects at human scales. Our brains, our intuitions, our language are all optimized for this niche. When we apply them to cosmology, they fail. The universe does not care about our intuitions. It operates according to laws that can be described mathematically, but not easily visualized or comprehended intuitively. This is humbling. It shows that reality is not obligated to make sense to us. It can be true, mathematically rigorous, observationally confirmed, and yet profoundly alien to our modes of thought. The expansion of the universe into nothing is one such truth. We can calculate it, measure it, predict its effects, but we cannot truly picture it in our minds. Some philosophers and scientists have argued that questions like, what is the universe expanding into, are meaningless, category errors that arise from misapplying concepts beyond their valid domains. The question presupposes an external space, and since no such space exists, the question is incoherent. This is a reasonable position, but it does not fully satisfy. The question arises naturally from how we think about expansion, and dismissing it as meaningless does not address the deeper issue. Our concepts of expansion, space, and existence are inadequate for describing the cosmos. Others have embraced the mystery. They argue that the universe's expansion into nothing is a profound reminder that reality transcends human comprehension. We are finite beings trying to understand the infinite, local observers trying to grasp the global three-dimensional creatures, trying to conceive of four-dimensional space-time. The fact that we can do so at all, even imperfectly, is remarkable, but we should not expect to fully comprehend everything. Some truths might be forever beyond the reach of human intuition, accessible only through mathematics. There is also a spiritual dimension to this question for many people. The universe expanding into nothing can feel like a metaphor for existence itself. We are here, we exist, but we're surrounded by non-being, by the absence of anything external. We are finite islands in an infinite or at least unbounded ocean of space-time, and there is nothing beyond the ocean. This can be terrifying or liberating depending on one's perspective. For some, it is terrifying because it suggests ultimate isolation. The universe is all there is, and it is expanding, and it will continue expanding forever, carrying everything farther apart until even galaxies lose contact with each other and the cosmos becomes cold, dark, and empty. We are alone in a universe that was not designed for us. That has no purpose, that simply is. For others, it is liberating because it removes the need for external validation. The universe does not need to exist within something else to be real. It does not need a creator or a container or a purpose imposed from outside. It simply exists, and its existence is sufficient. We are part of this self-sufficient cosmos, made of the same matter and energy, governed by the same laws. We are the universe observing itself, and that is enough. The expansion of the universe into nothing also raises questions about the nature of scientific inquiry. Science proceeds by asking questions and seeking answers. But what happens when the question itself is based on faulty assumptions? The question, what is the universe expanding into, is a perfect example. It sounds like a legitimate scientific question. It uses words we understand. It follows grammatical rules, but it is unanswerable because it presupposes something that does not exist. This shows that scientific progress is not just about finding answers, but about refining questions. Sometimes the most important advance is realizing that a question is malformed and needs to be reframed. Instead of asking what the universe expands into, we should ask how the geometry of space-time evolves over time, or how the distances between objects change, or what drives the expansion. These questions can be answered. The original question cannot. Ultimately, the expansion of the universe into nothing is a testament to the power and limits of human reason. We have developed mathematics and physics capable of describing phenomena we cannot visualize. We have built instruments to observe the cosmos on scales far beyond our senses. We have constructed theories that make predictions confirmed by observations. This is a monumental achievement. But we have also encountered the boundaries of comprehension. The universe is stranger than we can imagine, and some truths will always feel alien, counterintuitive, impossible to fully grasp. The expansion of space into nothing is one such truth. We can describe it, we can measure it, we cannot truly understand it in the way we understand ordinary objects and events, and perhaps that is as it should be. The universe owes us nothing, not even comprehensibility. While the standard model of cosmology, based on general relativity and the Big Bang, has been remarkably successful at explaining observations, it is not the only framework scientists have considered. Alternative theories have been proposed, some to address specific problems, others to provide radically different pictures of cosmic expansion. One persistent question is whether general relativity itself is the correct theory of gravity on cosmological scales. General relativity has passed every test in the solar system and in observations of binary pulsars, neutron stars, and black holes. But the universe is much larger than these systems, and it is conceivable that gravity behaves differently on cosmological scales. Modified gravity theories attempt to explain phenomena like dark energy and dark matter by altering the equations of general relativity. For example, some theories propose that gravity becomes weaker or stronger at very large distances, which could account for the accelerating expansion without invoking dark energy. Others suggest that the gravitational constant is not truly constant, but varies over time or space. These theories face significant challenges. They must match all the successes of general relativity in regimes where it has been tested, while also explaining the phenomena attributed to dark matter and dark energy. So far, no modified gravity theory has achieved this comprehensively. Most either fail to match observations, require fine-tuning, or introduce new problems worse than the ones they solve. Another alternative is the idea that the universe is not expanding at all, or not in the way we think. Some fringe theories propose that the redshift of distant galaxies is caused by something other than the expansion of space, such as light losing energy as it travels through space. This tired light hypothesis was popular in the early 20th century, but has been thoroughly ruled out by observations. It cannot explain the time dilation of distant supernovae, the pattern of the cosmic microwave background, or the abundance of light elements, all of which are naturally explained by expansion. There are also theories that propose the universe undergoes cycles of expansion and contraction. In cyclic models, the universe expands, reaches a maximum size, contracts back to a minimum size, and then expands again. The Big Bang would not be the beginning of everything, but just the start of the current cycle. These models face difficulties explaining what happens at the turnaround points and how information from previous cycles is erased or preserved. String theory, a framework that attempts to unify quantum mechanics and general relativity, offers some exotic possibilities for cosmic expansion. In string theory, the universe might have extraspatial dimensions beyond the three we experience. The expansion we observe could be confined to our three-dimensional slice of a higher dimensional space, or it could involve the extra dimensions in ways we do not yet understand. String theory also predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws. This has led to speculation about a multiverse, where our universe is just one bubble in an internally inflating cosmos. Loop quantum gravity, another approach to quantum gravity, suggests that spacetime has a discrete structure at the smallest scales, with a minimum possible length and a minimum possible volume. In this framework, the Big Bang might not be a true singularity, but a big bounce, where the universe contracted to a minimum size and then rebounded into expansion. This would eliminate the singularity problem and provide a more complete description of the universe's earliest moments. Despite these alternatives, the standard cosmological model remains dominant because it fits observations so well. The cosmic microwave background radiation, the abundance of light elements, the large-scale structure of the universe, and the accelerating expansion are all explained coherently by general relativity, plus the Big Bang plus dark matter and dark energy. No alternative theory can match this explanatory power with equal simplicity. Looking forward, the next generation of telescopes and experiments will test these models with unprecedented precision. The James Webb Space Telescope is already observing the earliest galaxies, probing conditions in the universe when it was less than 1 billion years old. Ground-based observatories like the Vera Rubin Observatory will survey billions of galaxies, mapping the large-scale structure and measuring the expansion history in exquisite detail. Missions like the European Space Agency's Euclid satellite are specifically designed to study dark energy and dark matter. By measuring how galaxies cluster and how their light is bent by intervening mass, these missions will constrain the properties of dark energy and test whether it is truly a cosmological constant or something more dynamic. Gravitational wave observatories, like LIGO and the future space-based LISA, will provide entirely new ways to probe the universe. Gravitational waves from colliding black holes and neutron stars carry information about the expansion rate, and future observations might detect gravitational waves from the inflationary epoch, offering a direct window into the first moments after the Big Bang. There is also the possibility of surprises. Past observations have overturned long-held assumptions and forced scientists to revise their theories. The discovery of cosmic acceleration was one such surprise. Future observations might reveal new phenomena that require rethinking the standard model. Perhaps dark energy is not constant. Perhaps the universe's expansion history is more complicated than we thought. Perhaps there are subtle signs of extra dimensions or quantum gravitational effects. The question, what is the universe expanding into, might also evolve as our understanding deepens. While the current answer is nothing, this answer is based on general relativity, which is a classical theory. A full quantum theory of gravity might reveal new aspects of space-time that change how we think about expansion. Perhaps at the quantum level, space-time does emerge from something more fundamental, a network of relationships or a holographic structure, or something we have not yet imagined. Or perhaps the answer will remain the same. The universe is expanding, but not into anything, because the universe is everything. This answer, while strange and counterintuitive, might be final. Some truths about the cosmos might be irreducible, not amenable to further explanation. The universe might simply be the way it is, and our task is to describe it accurately rather than explain it in terms of something more familiar. Either way, the search for understanding continues. Cosmology is one of the most dynamic fields in science, with new observations and theoretical insights appearing regularly. The expansion of the universe, once a shocking discovery, is now a cornerstone of our worldview. What other surprises await? What other features of the cosmos will shatter our assumptions and force us to rethink reality? These questions drive the field forward, ensuring that our picture of the universe will continue to evolve as we probe deeper into its mysteries. We have journeyed through some of the most abstract and counterintuitive concepts in all of science. We have grappled with the expansion of space itself, the absence of any external container, the horizons beyond which we can never see, and the acceleration driven by mysterious dark energy. We have confronted the limits of language, visualization, and perhaps even human comprehension. And yet, despite all this, we have gained something precious: understanding. Not perfect, complete understanding, but genuine insight into how the cosmos operates. We know the universe is expanding. We know this expansion is described by general relativity. We know it is accelerating due to dark energy. We know there is no outside, no container, no external space into which the universe grows. These are facts, confirmed by decades of observations, supported by rigorous mathematics, as real as anything we can claim to know. The universe is expanding into nothing because there is no thing for it to expand into. This answer, which sounds paradoxical, is simply a consequence of what the universe is: the totality of space, time, matter, and energy. When space expands, it does not displace anything or push into anything. It simply becomes larger, with distances between unbound objects increasing, driven by the dynamics of space-time itself. This is not an easy truth to accept. Our brains resist it. Our language struggles to express it. Our intuitions rebel against it. But it is true nonetheless, and learning to accept it is part of what it means to engage with cosmology honestly. There is a certain beauty in this answer. The universe is self-sufficient. It does not need anything beyond itself to exist or to evolve. It is not a thing within a larger framework. It is the framework. Everything that happens within the universe, according to laws that are intrinsic to it. We do not need to invoke external spaces or higher dimensions or anything beyond the cosmos to explain its expansion. This self-sufficiency is humbling and awe-inspiring. The universe simply is, and it is enough. It does not require validation or justification or grounding in something else. It exists and it evolves, and we are part of it, made of the same matter and energy, governed by the same laws. We are the universe observing itself, trying to understand its own nature. There is also a lesson here about the limits of knowledge. Some questions have answers, but those answers might not be comprehensible in the way we expect. The universe is under no obligation to conform to our intuitions or our linguistic categories. It can be true, real, and yet profoundly alien to our modes of thought. The expansion of the universe into nothing is such a truth. Science has given us tools to grapple with these truths. Mathematics allows us to describe phenomena we cannot visualize. Observations allow us to test predictions and confirm theories. Logic allows us to reason carefully and avoid fallacies. These tools are powerful, but they do not eliminate mystery. They reveal mysteries, make them precise, give us frameworks for thinking about them, but the mysteries remain. Perhaps this is appropriate. A universe we could fully comprehend that fit neatly into our intuitive categories would be a smaller, less interesting universe. The fact that reality exceeds our grasp, that the cosmos operates on principles we can describe but not easily imagine, suggests that we live in a grander reality than we might have hoped. As you go about your life, remember this: the ground beneath your feet is embedded in space-time, and that space-time is expanding, carrying distant galaxies farther away with every passing second. The expansion is not dramatic on human scales, not even on galactic scales, but it is real, measurable, relentless. Space is getting bigger, and there is nowhere for it to get bigger into. It simply is. You are part of a universe that is stranger than you can fully imagine, but not stranger than you can partially understand. You are a temporary arrangement of atoms that were forged in stars, held together by forces that emerged from the quantum vacuum, existing in space-time that is expanding according to equations written down by a patent clerk in 1915. You are a way for the universe to know itself, and that is extraordinary. If you enjoyed this journey through cosmic expansion, if you found value in confronting these difficult truths, hit that like button and subscribe. There are more mysteries waiting, more questions that will challenge everything you think you know, more truths that will expand your mind even as the universe expands around you, and we will explore them together, one video at a time, pushing at the boundaries of knowledge, living with the mysteries we can describe even if we cannot fully comprehend them. The universe is expanding into nothing, and that is okay. It is more than okay. It is profound, beautiful, and true. And understanding this, even imperfectly, makes us more than we were before. We are cosmologists now, citizens of an expanding cosmos, at home in a universe that does not need an outside because it is everything, and that is enough. Thank you for watching.